Fire may have triggered Mount St. Helens eruption. Could the fiery power of the sun have been the spark behind one of the most catastrophic eruptions in modern history? In 1980, Mount St. Helens erupted with unimaginable force, claiming lives and reshaping the landscape forever. While we've always looked deep within the Earth for answers, scientists now suggest we might need to look up to the sun. A groundbreaking study reveals a surprising connection between powerful solar flares and volcanic activity, hinting that the sun's energy might have played a critical role in triggering this historic event. What does this mean for our understanding of Earth's natural disasters? And could it help us predict future eruptions? Join us as we explore this extraordinary new theory and uncover the science behind it. The catastrophic eruption of Mount St. Helens on May 18, 1980 remains etched in history as one of the most devastating volcanic events ever recorded in the United States. The massive explosion obliterated over 230 square miles of forest, triggered landslides, and released a towering column of ash that rose more than 80,000 feet in the atmosphere. This disaster claimed the lives of 57 people, caused billions of dollars in damage, and left a scar on the landscape that persists to this day. Beyond the immediate devastation, it also profoundly impacted the fields of geology and disaster preparedness, offering critical lessons about volcanic behavior and risk mitigation. Traditionally, scientists have attributed the eruption to the intricate interplay of tectonic forces and internal volcanic processes. These include the buildup of pressure within the magma chamber and the seismic activity that typically precedes such an event. However, with new research that has opened an unexpected line of inquiry, suggesting that factors external to the Earth, specifically solar activity, may have played a surprising role in triggering the eruption. This hypothesis points to solar flares, immense bursts of electromagnetic radiation from the sun, as a potential catalyst for geophysical disturbances on our planet. Solar flares, among the most powerful events occurring in our solar system, are capable of releasing just as much energy as billions of nuclear bombs exploding simultaneously. These flares send high-energy particles and electromagnetic radiation hurtling through space. When these solar outbursts are directed toward Earth, they can interact with the planet's magnetosphere, the magnetic field that surrounds and protects us, causing geomagnetic storms. These storms have well-documented effects on Earth's technology, such as disruptions to satellite communications and power grids, but their influence on geological processes is less understood. A study presented at the European Geosciences Union, or EGU, General Assembly in 2018, provided compelling evidence of a link between solar activity and increased seismic and volcanic events on Earth. The researchers analyzed historical data and found that periods of heightened solar wind speed, a phenomenon tied to solar flares and coronal mass ejections, correlated with spikes in earthquakes and volcanic eruptions. According to the study, the influx of solar wind energy could disturb Earth's magnetic field, potentially altering the dynamics of magma movement beneath the surface. For Mount St. Helens, this suggests that solar activity might have amplified pre-existing tectonic and magmatic stresses, pushing the system towards its catastrophic breaking point. This groundbreaking research, though still in its early stages, has significant implications for our understanding of volcanic eruptions and seismic activity. It challenges the long-standing notion that such events are driven solely by internal Earth processes, instead introducing the sun as a potential external player. If confirmed, this solar volcanic connection could revolutionize how we monitor and predict natural disasters, adding a new dimension to geophysical science. The mechanism linking solar activity to volcanic eruptions represents a fascinating interplay between cosmic and terrestrial forces, driven by the interaction of solar-induced disturbances with Earth's magnetic field. Solar flares and CMEs are among the most powerful events in the solar system. These phenomena unleash immense bursts of high-energy particles, electromagnetic radiation, and plasma into space, intensifying the solar wind, a continuous stream of charged particles emitted by the sun. When these powerful particles reach Earth, they collide with the planet's magnetosphere, a protective magnetic shield that deflects most solar wind energy. However, under the impact of powerful solar events, this shield can become temporarily disturbed, leading to geomagnetic storms. These storms are characterized by sudden fluctuations in Earth's magnetic field, often manifesting in visible phenomena such as auroras. While their atmospheric and technological impacts, such as disrupted satellite communications, power grid failures, and GPS interference, are well documented, their potential interference and influence on Earth's internal geophysics remains an emerging area of study. Geomagnetic storms have the ability to induce electrical currents in conductive materials on Earth, including in magma reservoirs beneath the crust. These currents, known as telluric currents, can generate localized heating, which might subtly alter the temperature and viscosity of magma. Warmer, less viscous magma becomes more buoyant, making it easier to ascend toward the surface.
There's something about
In addition to heating effects, geomagnetic disturbances could also create variations in stress within the Earth's lithosphere. The crust and upper mantle are already subject to complex forces from tectonic plate movements, and even small perturbations from geomagnetic currents might be sufficient to tip these forces into instability. For instance, a slight redistribution of pressure within a magma chamber could increase the likelihood of a breach, triggering an eruption. Another intriguing hypothesis is that geomagnetic storms could enhance the movement of volatile gases dissolved in magma. These gases, such as water vapor, carbon dioxide, and sulfur dioxide, are critical in driving volcanic eruptions. If geomagnetic disturbances promote the release or expansion of these gases, they could accelerate the buildup of pressure within a magma chamber, hastening the onset of an eruption. It is important to emphasize that solar activity alone is unlikely to directly cause volcanic eruptions. Instead, it might serve as a catalyst, amplifying conditions that are already ripe for an eruption. Volcanic systems are inherently complex, influenced by a range of factors including tectonic stress, magma composition, and local geology. Solar-induced geomagnetic storms could act as an additional layer of influence, pushing a system already on the edge of instability into eruption. The potential effects of solar activity are likely to be most significant in regions under considerable tectonic stress, where volcanic systems are already near critical thresholds. In these areas, even minor external perturbations could have outsized impacts, potentially altering the timing or intensity of eruptions. This raises intriguing possibilities for predicting volcanic activity by monitoring not only terrestrial conditions but also space weather events such as solar flares and CMEs. The idea that the sun's powerful outbursts might influence the Earth's deep interior opens a new frontier in geophysical research. If further studies validate this connection, it could revolutionize our understanding of the interconnectedness between Earth systems and the cosmic forces at play in our solar system. Such insights might one day enhance our ability to forecast volcanic eruptions, potentially saving lives and mitigating the impacts of these powerful natural disasters. The eruption of Mount St. Helens in 1980 is a textbook example of a volcanic event driven by internal geological forces, including magma buildup, tectonic movement, and gas pressure. However, the potential role of external solar influences introduces a new and intriguing dimension to its causation. If solar flares and associated geomagnetic disturbances did play a role in exacerbating the conditions leading to the eruption, it would significantly alter how scientists approach volcanic risk assessment. This hypothesis suggests that the sun's activity, typically considered an atmospheric or space-related concern, might also have terrestrial implications extending to the deep Earth. Such a connection would be groundbreaking, as it redefines the boundaries of interactions between cosmic phenomena and geological processes. For Mount St. Helens, this raises compelling questions about whether heightened solar activity could have contributed to the timing or intensity of the eruption. Could geomagnetic disturbances have subtly affected magma dynamics beneath a volcano, accelerating processes already nearing a critical threshold? While direct evidence for such a link remains sparse, the possibility invites a deeper exploration into the interplay between solar and volcanic systems. The broader implications of this theory are equally profound. If confirmed, it could lead to a paradigm shift in volcanic monitoring and risk assessment. Scientists might need to reevaluate current methodologies, incorporating solar activity as a potential factor influencing volcanic behavior. This would involve integrating geomagnetic data with traditional geological and seismic observations, potentially enhancing the accuracy of eruption forecasts. Moreover, this theory underscores the interconnectedness of Earth's systems with cosmic phenomena. It highlights the need for a multidisciplinary approach to understanding natural disasters, one that bridges the gap between geology, astronomy, and atmospheric sciences. Such an approach could uncover previously overlooked links, enriching our comprehension of Earth's dynamic processes. For Mount St. Helens and other volcanoes worldwide, this hypothesis opens a new frontier in volcanology. It prompts scientists to look beyond traditional Earth-bound explanations and consider the broader cosmic context in which our planet exists. While the idea of solar influences on volcanic activity remains in its infancy, its potential implications are vast, offering exciting opportunities for research and discovery. By expanding the scope of volcanic studies to include external cosmic factors, scientists could gain a more holistic understanding of the forces shaping Earth's surface, and perhaps improve humanity's ability to predict and prepare for future eruptions. Likewise, here are a few notable volcanic eruptions where this hypothesis might be worth exploring in more depth. The eruption of Eyjafjallajökull in April 2010 caused widespread air travel disruption across Europe. Interestingly, this event coincided with a period of increased solar activity following a prolonged solar minimum. Some researchers have speculated whether geomagnetic storms or fluctuations in Earth's magnetic field induced by solar activity could have influenced subsurface magma movement. Although current scientific consensus attributes the eruption to tectonic processes related to the spreading of the mid-Atlantic ridge, further studies could explore potential solar-terrestrial interactions. Next, Mount Pinatubo's catastrophic eruption in June 1991 was one of the largest volcanic events of the 20th century. It occurred during a period of heightened geomagnetic activity linked to intense solar flares. While the eruption was primarily driven by tectonic subduction processes and magma buildup, researchers might investigate whether solar-induced geomagnetic fluctuations played a secondary role in altering the volcanic's magmatic pressure or crustal stress conditions. This line of inquiry could involve analyzing historical solar activity data leading up to the eruption. The eruption of El Chichón in March and April of 1982 was a surprise event that caused significant climate impacts due to the release of sulfur dioxide into the stratosphere. Historical records indicate moderate solar activity during that time. Although no scientific link has been established between the eruption and solar influences, the sudden and relatively unexpected nature of the event might provide a case study for examining how external forces, including geomagnetic storms, could affect volcanic systems already under internal pressure. Taal Volcano's dramatic eruption in January 2020 prompted large-scale evacuations and disrupted life in the surrounding areas. This event took place during a phase of fluctuating solar activity, though no official studies have linked the eruption to solar influences. Given the Philippines' geologically active setting, where both tectonic and volcanic triggers are frequent, future interdisciplinary research could assess whether solar-relegated geomagnetic fluctuations might exacerbate magmatic or hydrothermal processes in sensitive volcanic systems. While these cases remain speculative, they highlight the potential for exploring solar-volcanic interactions. The field would benefit from more comprehensive data sets, including long-term monitoring of of solar activity, Earth's geomagnetic responses, and volcanic behavior patterns. Understanding whether solar activity might play even a minor role in triggering volcanic events could advance both Earth science and space weather research. Likewise, earthquake scenarios occurring during solar maximum periods have sparked significant scientific interest as they raise questions about the potential interplay between solar activity and seismic events. Solar maxima, characterized by heightened sunspot numbers and increased solar electromagnetic activity, often lead to intensified geomagnetic disturbances in Earth's magnetosphere. While tectonic processes are undeniably the primary drivers of earthquakes, the coincidence of several major seismic events with peaks in solar activity has prompted researchers to examine whether solar-induced electromagnetic fluctuations might influence Earth's crustal stress dynamics. One of the most notable examples is the Great Alaska Earthquake of 1964, a magnitude 9.2 event that remains one of the most powerful earthquakes ever recorded. It struck during the solar maximum of solar cycle 19, a period noted for its extreme solar activity. While the earthquake was predominantly caused by tectonic plate subduction along the Alaska Aleutian megathrust, some researchers have hypothesized that intense geomagnetic disturbances at the time could have played a secondary role. These disturbances, which result from interactions between solar wind and Earth's magnetic field, might theoretically influence stress distribution in tectonic plates or even affect the behavior of fluids within fault zones. The Sumatra-Andaman earthquake of 2004, which had a magnitude of 9.1 to 9.3 and triggered the catastrophic Indian Ocean tsunami, provides another compelling case. Although this earthquake occurred shortly after the solar maximum of solar cycle 23, scientists have considered the possibility that lingering geomagnetic effects from the preceding solar peak might have contributed to stress accumulation along the fault line. This earthquake, which ruptured a massive segment of the subduction zone, has been the subject of studies investigating whether solar-driven geomagnetic variations could subtly amplify pre-existing tectonic stresses. Similarly, the Tohoku earthquake in Japan in 2011, a magnitude 9.1 event that caused widespread devastation and a massive tsunami, coincided with heightened solar activity during the ascending phase of solar cycle 24. This coincidence has led to speculation about whether solar-induced electromagnetic fluctuations could influence the stress environment of Earth's crust. Some studies suggest that variations in Earth's magnetic field induced by solar activity might interact with subsurface electrical currents or fluids, potentially affecting fault stability. While the connection remains theoretical, the timing of the event has fueled ongoing exploration of the topic. The Chile earthquake of 2015, a magnitude 8.3 event in Illapel, also occurred during a period of increased solar activity. This earthquake, like others, has been analyzed in the context of solar-induced geomagnetic disturbances. Though a direct causal relationship between solar activity and seismic events has not been definitively established, scientists continue to explore whether the dynamic coupling of Earth's magnetosphere and lithosphere during geomagnetic storms could influence fault behavior, especially in regions already under significant tectonic stress. These examples highlight the persistent scientific curiosity about the possible links between solar activity and earthquakes. While direct causality remains unproven, the patterns observed have inspired multidisciplinary research into how geomagnetic disturbances, ionospheric anomalies, and solar-induced electromagnetic variations might interact with Earth's tectonic processes. This line of inquiry represents a fascinating frontier in understanding the complex forces shaping our planet. Research into the potential links between solar activity and seismic events has garnered considerable attention in recent years, as scientists seek to understand whether phenomena associated with solar maxima might influence Earth's geophysical processes. A review published in Earth and Planetary Science Letters in 2017 conducted a detailed analysis of historical earthquake records to investigate patterns in seismic activity. The study observed a possible clustering of significant earthquakes during periods of high solar activity. While this finding sparked interest, the researchers emphasized that the statistical significance of the observed patterns was marginal, urging caution against overinterpreting the results. This underscores the complexity of isolating solar activity as a potential contributing factor in seismic events. Building on this line of inquiry, a study published in Natural Hazards and Earth System Sciences in 2020 analyzed seismic and geomagnetic data spanning 4 solar cycles. This research found a weak but noticeable increase in the frequency of global seismic events during intense solar maximum phases. However, the correlation was not strong enough to serve as a reliable predictive tool, further illustrating the challenges of linking solar activity directly to earthquake occurrence. This weak correlation highlights the importance of refining analytical methods and improving the quality and resolution of long-term data sets. Focusing on regional dynamics, a study in the Geophysical Journal International in 2019 examined earthquake-prone regions such as the Pacific Ring of Fire. This region, known for its tectonic activity, provided a compelling case study for exploring the relationship between solar activity and seismicity. The findings revealed a slightly higher occurrence of moderate to strong earthquakes during peak periods of solar activity. Although intriguing, the results remain insufficient to establish causality, serving instead as a basis for further exploration into potential mechanisms. Despite these findings, establishing a definitive link between solar activity and earthquakes has proven to be a significant challenge. Earthquakes result from highly complex geological processes, including tectonic plate interactions, mantle convection, and the buildup and release of stress in Earth's crust. These processes operate independently of solar influences, making it difficult to discern any subtle effects that solar activity might have on Earth's geophysical systems. Moreover, the lack of long-term, high-resolution data on both seismic events and solar phenomena poses a significant limitation. Reliable data sets covering multiple centuries are necessary to identify and validate potential patterns or correlations. Additionally, there is the ongoing challenge of distinguishing coincidence from causality. Earthquakes and solar storms are both frequent occurrences occurrences, and any apparent correlation between them could arise purely by chance. Without a clear mechanism linking the two phenomena, the possibility of coincidence remains difficult to rule out. Furthermore, the multifactorial nature of earthquakes complicates the attribution of any singular influence. Earthquakes are shaped by a confluence of factors including atmospheric pressure variations, oceanic movements, subsurface fluid dynamics, and the inherent instability of tectonic plate boundaries. Solar activities, if it plays a role at all, is likely just one small piece of a much larger puzzle. Stay tuned for more updates as scientists delve deeper into these groundbreaking investigations. And don't forget to like, comment, and subscribe for more content.